All right, looks like we're recording. Okay, so we're going to talk about chapter 15, which is on sampling distributions. Okay, now remind me, I know we talked about these, but they were like the first week of class, so everybody's forgotten, right? What is the definition of a sample and a population?
Population is every single thing possible within what you're studying.
Right, the entire set of individuals. And the sample is
A representative portion.
a subset of the population. Okay, hopefully a representative, but not necessarily. Also remind me, what is parameter and statistic? Okay, do you remember that one? Either of those?
Parameter is a number that describes the population.
You threw your voice, didn't you?
Going everywhere.
What did they say?
True value of the population.
That's right, true value of the population. And the sample is?
Numerical summary of.
James, remember the sample?
Sample is a subset.
Sorry, the statistic, that's what I meant.
It's just a statistical value of the.
Can't use statistical and statistic.
Just a numerical.
All right. Yeah, numerical value.
Numerical value of what?
For the sample.
The sample. Okay. And last time we talked about the law of large numbers. Remember what that was, Philip? It's all review so far. It's an easy chapter. Remember, Philip?
Pardon?
What's the law of large numbers?
The what?
Law of large numbers.
The population.
No. We learned about it last time in class. Except for you've already forgotten. Remember, Aaron?
Nope.
Uh-oh.
I know it now.
Chandler remembers. Oh my gosh.
I don't know.
That was our big finale. That was because you left early. Christian,
Isn't it why the casino always
I
wins?
wasn't here last time.
you didn't watch the video either? Well, what's your problem? Dalton, save me. Oh my gosh. I have failed as a teacher. Nobody even rewatching the reruns. Come on. Alex.
So it's between the sets why the house always wins, right? It's like
Why the house always wins. That's the easy definition.
yeah, it's when the more repetitions you do, the closer that your observation gets.
Yeah, perfect. Okay, who's studying with Alex? He's the only one that remembers. Who wants to ace the test? Do you have Alex's contact info so you can study tonight?
I actually do.
The more repetitions
Yeah.
you do, the closer it gets to the theoretical.
Well, at least that's a lot better than the definition of the book. I made it confusing.
Yeah, isn't that nice? Okay. So this whole chapter, we're going to go deep into the law of large numbers. Now, I should have mentioned this last time, but I've got a lot of really good quotes. You know Penn and Teller?
Yep.
Okay, Teller never says anything, it's only Penn, so this is just Penn. But he said that Las Vegas was built for people who are really bad at math. You don't know who Penn and Teller are?
They're famous magicians and they have a show at the Rio. And they also do that full TV show.
And Penn and Teller does not talk at all.
So don't they like hate each other too?
Not
They
really.
like have a professional relationship, but they don't actually like each other.
Yeah, I don't really see many alliances.
All right, so this quote here that I'm about to read comes from LasVegasForNewbies.com. Okay? There are no casino games or bets where the house does not have a clear advantage. The odds either favor the house or they get a commission. And if you are not familiar with the basic information about the games you play or the bets you make, you are just about a guaranteed loser. In short, casino owners are in business to make a profit. They did not build all those gorgeous hotels by giving away money. Now, why do you think they give you free alcohol?
Because you lower your inhibitions and you make stupider
Because you
choices.
make stupider choices, okay? All that free alcohol just goes in their pocket, okay? Now, let me see here. This website I want to show you, but the article's been taken down, but I think, hopefully, the headline is still here. Let's see here.
Some guy did make over $1 million on a $5 side bet though the other day at Caesars.
Oh, wow, they've actually fixed this.
That's awesome.
You see the headline there?
That's great.
Okay. You're more likely to get struck by lightning than to win the lottery. And this poor guy did. Yeah. Well, he didn't win the
Yeah,
lottery.
he said he's after buying lottery tickets.
Well, he did not win the lottery. He was struck. Anyway. So, all right. So the real thing that I want to talk about, all this has been review up to now, is I want to stop screen sharing. There we go. We're going to talk about one of the most important theorems in all of statistics, and it's called the central limit theorem. And the idea here is, regardless of the underlying distribution, the sampling distribution of, and I'm going to put this in parentheses, of p hat or x bar becomes approximately normal as the sample size increases. Okay?
P bar or X bar?
P hat or X bar. Okay? Now, what I would like to do is I'm going to do a simulation. Okay? Now, before I do that, how large is large enough? That becomes the key question. Okay? And I'm going to give you two different answers. Yeah. Okay? And well, before I do that, it depends on the type of data. Okay. Now, a lot of you like to memorize one rule, but I'm going to be giving you 3 rules eventually. I'm only 2 today, but eventually I'm going to give you a 3rd one. Okay. Now, if you're doing an X bar, okay, generally speaking, n should be greater than or equal to 30. Although sometimes you can get away with smaller than that. Okay. If you're doing p hat, okay, proportional data, then you need NPQ greater than or equal to, make sure I mess this up, 10. Okay? So, that's what I'm going to be giving you. Okay? This is a good test question, by the way. Some of you are going to pick one, but not the other. And the answer is, it could be either one. There's going to be another test that I'm going to give you that's going to have a different rule altogether, but it doesn't really apply to the central limit theorem. Okay? So let me give you an example. Go ahead. Oh, well, I guess we could have gone to the library today, but I didn't think about it. You really don't need to go to the library, but if you have a computer and you want to follow along, you can, although it's not necessary. Okay? Let's say, I'll write this on the board before I go. Okay? We're going to do a simulation. Okay? And the simulation that we're going to do is the IQ test is normally distributed with a mean equal to 100 and a standard deviation equal to 15. Okay? Now, I do not have actual scores, but I'm going to simulate scores. Okay? So I'm going to try to do a simulation here. And you can follow along, or you don't really need to, though. So for those of you who have Excel and you want to follow along, feel free. Okay? So what I'm going to do is I'm going to do a bunch of random numbers, rand between 75 and 125. Okay, so these are just going to be a bunch of random numbers. Now, oh look, I got 100 right off the bat. I'm going to copy this over 1, 2, 3, 4, 5, 6, 7, 8, 9.
These are IQ scores.
These are pretend IQ scores. Okay, and now I'm going to go down 100 rows. Okay, so I've got 900 students, pretend. Now, remember, when I type, these are going to change every time, right?
So do you copy these?
So I'm going to highlight all of these, and I'm going to say copy, paste special, click on the 1, 2, 3, and now when I type, they don't change anymore. Okay? Now, let me ask you all a question. If I had a bunch of random numbers based on what I've talked about in this class before, if I were to make a histogram, what would it look like? Would it be normally distributed, random numbers?
No.
No, it would not be.
It would not be big enough?
No, it's plenty big. It's 900, right? Random numbers. You got a bunch of random numbers. Are any numbers, so a normal curve, remember a normal curve would say we're going to get more 100s than we are 75s or 125s, right? That's what you're saying if you're saying it's going to look like a normal? But if they're random, is it supposed to look like a bell curve?
No.
Oh, All the numbers come at equal rates, right? What would that curve look
A
like?
big box.
Yeah, it would look like a box. Okay. 75, 125, right? Should look like a uniform distribution, they call this. Okay. Now, I hate the histogram maker, but because I'm in a little bit of a hurry, we're going to see how good or bad this thing is. I'm going to highlight all my data, and I'm going to make a histogram, and we're going to see if it looks like a box, and hopefully it does. Insert recommended charts, all charts, histogram. Yeah, it's a crappy thing. Okay, it's supposed to, it looks kind of like a box except for this last thing, right?
Because of outliers? Or they just
No,
make
it's
it bad?
because their histogram maker sucks. Okay? But yeah, except for the last column, it looks like a box, right? Roughly?
So don't use this on the test.
Don't use this on the test. This is a perfect illustration why their histogram maker sucks. I might show you another definition. But yeah, so pretend that last bar is not there. That does look sort of like a box, right? Okay? All right, if you were to do this yourselves, you probably would create your own units of 75 to 84, 85 to 94, et cetera, and then it would look more like a box. But the computer one just doesn't work very well. Okay, but I did want to show you that it looks roughly like a box. Okay, now here's what I'm going to do with this little experiment. Okay, first of all, I'm going to insert a blank row, and I want you to tell me what you think the mean and the standard deviation should be. Okay, now based on what I told you, well, let's back up here. If it looks like this, right? Maybe I'll stop sharing so you can see the board. Okay, it looks like this box. If you were to guess what the mean would be, what would you guess? Probably right in the middle, right? Around 100? You'd guess the mean to be right in the middle, right? Okay. Well, let's find out what the mean is. Okay, and which mean is this if I do all the 900 students? Would be a population mean. What's the command? Average, and then go wash out your mouth, right? Okay. Okay, so this is supposed to be about 100. Drum roll, please.
This looks like more around like
100.07, that's pretty cool, right? Okay. Now, the standard deviation, according to what I wrote on the board, the standard deviation should be what? Should be 15. Now, this is a simulation, so I don't know if I'll get exactly this, but what's the command for the standard deviation? Which one do I pick? P, because I'm doing all 900 students, right? Pretend this is a school of 900. So I'm going to do the population. Okay. Now it's supposed to be about 15. Let's see how good it does. 14.8, pretty good simulation, huh? That's what I'm talking about. All right, so that's pretty close to my simulation here, right? Except for, clearly this is not a normal distribution, right? We did our histogram and it does not look like a bell curve. Okay? Now let's pretend that that each row represented a random sample of 9 students. Okay? So if I did a random sample of 9 students, I could find the mean, which is what command, Aaron? Say it again. What is the mean of the first 9 students? What's the command? How do I find the mean?
Oh, equals.
Average, there we go. Okay. All right, so I did a random sample of 9 students. I got a mean of 102, which is a little bit higher than my 100, right? Okay. I'm going to copy this down. We're going to pretend that we did 100 random samples of 9. Okay. All right, so if we go up here, so I got 102.5, I got 98.5, 102, 103, 109. That one's pretty high, right? 102, 97, 99, 98, 87. That one's really low. It's a lot lower than you would expect, right? Okay. So there's a lot of variation going on, right? Okay. Now my question to you all is, if I were to do a histogram of all 100 of these means, according to the central limit theorem, what should it look like?
Approximately normal.
Okay, so do you think, even though the population is not normal, will my sampling distribution become normal? Who thinks it will look like a bell curve? 1, 2, 3. Who thinks it will not look like a bell curve? 1, 2, 3, 4. Okay. All right. I'm gonna, because I want to be a little quicker here, I'm going to cheat. I'm going to insert my histogram maker, all charts, histogram. What do you think? What does that look like? It looks roughly like a normal curve, right?
So if you did the standard deviation for those ones, would you use the?
Oh, you're jumping ahead of me. We're going to answer that question in just a minute, okay? All right, so this is a really good illustration of the central limit theorem. Even though the underlying distribution is not normal, if you take a mean of all the means, it will become, the sampling distribution will become normal. This is why the normal distribution is our most important distribution, because we're using a uniform distribution, we're using a normal distribution to simulate it, right? Okay?
Okay, so
Now,
even though an underlying distribution is not normal, if you take a sampling distribution, which is the mean of all the means, then the distribution will become normal.
correct. Okay, so that's what I just illustrated, okay? And just for fun, we do this one more time. And I hate this histogram maker, but it's nice because it's a lot faster, okay? So just to compare here, all charts, histogram, okay? You can clearly see, maybe I'll pull this up a little bit here. This is the population distribution, and this is the sampling distribution. Okay, now, okay, so you can kind of compare and say, wow, yeah, we've got a box here, we've got a bell curve here, right? Okay. Now, my question to you all, if I were to do a mean of the means, okay, my question is, if I were to take the mean of all 100 of these sample means, okay, I'm not going to press enter yet, and don't you either. I want you to think about this for a minute. Okay, so my population mean was 100.07. Okay, if I do a mean of my means, will I get exactly 100.07, or will I get a number that's different than 100.07? Who thinks it will be exactly the same? Nobody? Who thinks it will be slightly different?
Slightly different.
Okay, so most of you think it will be slightly different. Here we go with the drum roll. Is there enough suspense yet? It's exactly the same. What? Now, here's what's cool about this. Let me explain what's going on. Okay? So I've got my, this is my population distribution here, right? It's a rectangle. Now, Jordan was pretty astute and said, I think that the mean will be somewhere in the middle. Okay? And he was right. Now, so this blue, where did I put my blue? this blue represents the population mean, mu equals 100. Okay? We use the letter mu when we're talking about the population. Okay? What we've just done is we've done a sampling distribution of X bar. And that's the red curve there. X bar looks normally distributed, and it also has a mean of 100 as well. Okay? So what we say when these match here, X bar is an unbiased estimator of mu. Okay? Now, how does this apply to your survey, which I haven't heard back from the IRB, but hopefully I'll hear back from them in the next day or two. Okay? By the way, yeah. So, it's unbiased in that we got the exact same value, right? Okay? So, as we look at this, remember, now by the way, it says that my n is supposed to be greater than or equal to 30. I'm actually doing this with an n of 9. Remember, each of my random samples are 9. So sometimes you can get away with smaller numbers than 30. But as a general rule, that's why I asked you to have at least 30 in all of your sampling distributions. And hopefully you guys can start collecting data on that shortly. Okay? So now we're going to go back to, I don't want to stop broadcast, I want to stop the screen share, or start the screen share. Now we're going to answer the other question, Bettina's question, okay? Now I got a standard deviation of 15 almost, right? Now my question to you all, if I did the standard deviation of the means, now which one should I use? I'm going to use sample because all of these means are samples, right? Okay.
And the formulas, that's the one with square root of n.
Well, so this is going to n minus 1 rather than n. So the population we use n, the standard deviation we use n minus 1. But my question to you, if you're dividing this by 100 or 99, is it going to make a big difference? Shouldn't make a big difference, right? Now, my question to you all, though, is, and don't press enter if you have your thing here. Okay, so the population standard deviation was almost 15. Do you think that this sample standard deviation will be close to 15, or will it be different? Who says it will be close to 15?
Like
1, 2, 3,
from that
4,
previous
5.
number, or?
Yeah, 14.8. Is it going to be close to 14.8? So we got about 8 people. Who says it's going to be different? 1, 2, 3. Okay, here we go. Drum roll, please. Here comes the suspense. It's really different, isn't it? It's a lot lower. Okay. Now, there is a relationship between the two. And this kind of goes back to that formula I showed you guys a little bit earlier. Okay. And the difference is if I take my population standard deviation and if I divide it by the square root of n, now each row is a random sample of how many students? 9. So I'm going to put n is 9 here. These two numbers, 4.74 and the one I'm about to find, are going to be very close to each other. Okay? So 4.7, 4.9. See, those are fairly close, right? Do you see that? Okay. And so, do you remember a few days ago, I remember I gave you 2 different formulas. Where's my eraser? For the z-score. Remember, I gave you the formula z equals x minus mu over sigma. I gave you z equals x bar minus mu over sigma over the square of n. Do you remember that?
Yeah, over sigma is for the population, and over sigma over square root of n is for
For the
the sample.
sample, right? And I told you kind of ignore the x and the x bar. Well, now you shouldn't ignore them anymore. Okay? So if you're dealing with a sample, you're going to use this formula here. Now the difference is, previously, when we were using this formula here, the n was always 1. And if your n is always 1, these formulas are almost identical, right?
Yep.
After today, your n will not always be 1. And so you want, that's why I said this is the better formula to remember. Okay? So if you have an n in your formula, that means the central limit theorem probably applies, and we're going to be using this formula here. Okay? But it does refer to, remember, x bar refers to what? Your sample mean. And mu refers to population mean. Now, some of you kind of screwed those up on the last test. Okay? This becomes a critical skill from this point on, because screw them up, you're probably going to screw that up, and you might mess up your sign. It might be negative instead of positive, or vice versa. Okay? So you've got to be able to identify your sample mean and your population mean from this point on. This skill becomes critically important for the rest of your class. Okay? Now, we talked about this, okay? Let me go back to here for a minute. How large is large enough? It depends on your type of data. If you're using continuous data, we talked a little bit about that, you're going to use x bar greater than 30, although you can see we got away with 9 in this case. Sometimes there are times when you can get away with a lot smaller, but generally you want your n to be greater than 30. Now let's talk about the discrete, or what the book refers to as the finite distribution. Okay? P hat refers to what?
Population something. I don't know. Population.
It's not, well, they really like the letter P, and this does not actually refer to population.
Is there a distribution?
Standard deviation.
No. Since you mentioned standard deviation, let me back up here for a minute. We've got sigma and we got S. What's the difference between those two? Which one's the sample?
Sigma is a standard deviation.
Which one's the sample, Philip?
The second one.
The second one is the sample what? Standard deviation. And the first one is the population standard deviation. Okay? Another critical skill that's even going to get more critical as time goes on. We've got to be able to distinguish between the population and the sample. Okay? It affects the formulas that we pick. Very, very important skill. If you haven't mastered it now, you better master it this week, or this class is going to get real hard. Okay? Now, let's talk a little bit about P and P hat. Okay, we haven't talked about those letters too much. But in a way, they're similar to the sample mean and the population mean, but they're not means. Okay? And it refers to discrete data. Okay? These are discrete. Actually, we might even call them binomial, which means you only have two choices. Okay? Yes, no, true, false, heads, tails, that kind of a thing.
What's the name of the other P, the bottom one?
P hat.
P hat.
So the P is discrete and the P hat is binomial?
No, they're both discrete, they're both binomial. P stands for proportion. P hat stands for sample. Actually, I should have called this population proportion and sample proportion. Population proportion and sample proportion. Okay, so P stands for proportion, not population necessarily. Okay, not to be confused with p-value. I don't know why statisticians love the letter
Remind
P.
us again one more time, what was the p-value? Just say it.
What was the
Just
p-value?
say it quick.
I want you guys to remember.
We should say the right one.
P-value is the area under the curve, to the right side or to the left side, as the case may be. Okay? All right, so now when we're dealing with P's and P hats, NPQ must be greater than or equal to 10. So you're not looking at simply the n, but notice there's an n in both of these, but with the proportion you have to take into account the P and the Q. Okay? So what'd you say?
Why does it Q?
Oh, Q, I didn't tell you what Q was. Okay? P equals the probability of success. And Q equals the probability of failure.
Population proportion.
To the population proportion. Okay? So Q equals 1 minus P by the complement rule, right? If you succeed 60% of the time, how much do you fail? 40% of the time, right? So that's just simply the complement rule. So that's what Q is. Okay?
What did, I can't see what you said.
Q is 1 minus P.
Yeah.
Okay? Now, okay, so here's what I would like to do. What I would like to do is another couple of simulations. Sorry, I need to share my screen. This standing is going to kill me, I swear.
Show me the Instagram one more time.
What'd you say?
Can you show me the Instagram one more time?
I'm going to show you right here in a minute. Okay? Now, part of me wonders if I should do this. All right, I'm going to just do something really quick here. You don't need to know this formula.
Don't need to know the formula.
You don't.
That's a good one.
Okay, so I know dist number of successes, this number of trials is 5, probability of success 0.3. Okay, so this is kind of a simulation that I'm doing here. Okay, now, so some of the key parameters that I want you to notice here. My n is 5. My p my probability of success is 0.3. Therefore, my q equals 0.7. And what I'd like to do is I'm going to create a histogram, insert bar chart 2D. Oh, I screwed up. I forgot to put apostrophes here.
So you didn't do apostrophes. Did you do apostrophes with the last histogram?
No,
Or not?
because I was just using, I was just graphing column K. Okay, I didn't group it. I let it group it itself. Okay, so insert bar graph 2D. Does that look normally distributed to you? It's pretty skewed, right? Okay, Now I'm going to do the same thing, except for this time, I'm going to go down here. I'm going to go to 10 this time. And I need to change this. Okay, so the same sort of thing this time. My P and my Q are going to be exactly the same, but I've changed my N from 5 to 10. Okay? When I create my histogram this time, what do you think? Does that look more normal? It's still a little bit skewed, but it looks more normal than the first graph, right? Okay. Now, by the way, I want to check my NPQ. So if I take my N times my P times my Q, that gives me, is that value greater than 10? No. Okay. If I copy it down here, but is that value greater than 10? No. Okay. Now what I'm going to do is I'm going to copy these, but I'm going to change it to 100 this time. According to this, my 100, now it's well greater than 10, right? Except for I've got to finish my thing down here. Whoops. Changed the wrong one. Let's try this one, 100. Okay. Now, insert chart 2D, quick layout. What do you think of that now? Does that look normally distributed?
That's really good.
Sure does. Okay. So you can kind of see how things change. In fact, this is almost perfectly symmetric. This one's still pretty skewed, right? Relatively skewed. This one's definitely skewed. Okay. So this also illustrates the different types of data. Okay. So you can think of, as we're doing our projects, this data here with the mean, you could think of that as your potato data or your speed limit data. You're calculating a mean, your N should be greater than 30. That's why I want you to do 30 bags or 30 cars or something like that. This here represents your polling data, okay? Now, that's why I want you to have a much larger sample than 30, although I'm letting you get away with just 30 on the phone calls because I know that's going to be a pain in the butt. Okay? Really, you should have a lot more than 30, but I know it's hard, so if you can get 30 answers, I'm going to call it good. Okay, but it really should be a lot more than that. Okay? But as your sample size increases, the law of large numbers kicks in, the central limit theorem kicks in, and you can see that your data become normally distributed, even though the underlying distribution was not very normal. Okay, does that make sense? All right, so what I'd like to do is I'd like to do a couple of examples here. Okay, and I'm going to do it here so that you can see my hand, read my hand, or my typing better than my handwriting. Okay. So let's say that the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain is known to be strongly right skewed. An obstetrician in low income neighborhood obtains a simple random sample of 35 women and finds the mean weight gain to be 36.2 pounds. Should she be concerned her patients are gaining more weight than the population? Okay. Now, before we draw this, well, actually, before, sorry. Let's go through, this is a really good skill that you guys might want to do. And what we're going to do is we're going to label, hopefully properly, all of the numbers in here. Okay? The mean weight gain during pregnancy is 30 pounds. Something equals 30. What is the something? What?
Okay.
The mean? Is that what you said? Which mean? Is it mu?
Oh.
Is this the population mean?
Yeah.
So I'm going to use mu equals 30 pounds. I would recommend when you all are doing this to identify this stuff first. It'll make your life easier. Okay? Mu is going to equal 30 pounds. With a standard deviation of 12.9, what is 12.9? Which standard deviation is it?
It's that six.
The population standard deviation, so I'm going to use that sign, which is called sigma. Sigma equals 12.9 pounds. Okay? Because these are both populations, right? Population, population. Okay? Weight gain is known to be strongly right skewed. Rather than draw this on the board, I'm going to draw this on here. What does right skewed look like? If I were to draw this, tell me what I'm drawing. What does right skewed mean?
There, it's the one, go up. That one right there. That was beautiful.
Does that look normal to you? No, good. I was worried it would. Okay, it's right skewed. Okay. So it's not, so what we're saying when we're saying it's right skewed, is it normally distributed? Should not be. The population is not normally distributed. Okay? All right, obstetrician in a low-income neighborhood contains a simple random sample of 35. What's 35? Sample size, what letter do I use for sample size? Nope, not S. Nope.
E?
Nope.
We don't know.
You should. On the board. N, right? Is my N greater than 30? So my N equals 35, right? Which is greater than or equal to 30. So the central limit theorem applies. Okay? All right. A mean weight gain is 36.2 pounds. What is 36.2? That's X bar, right? X bar equals 36.2, and it's X bar because this is the sample, right? Okay. Should she be concerned about her patient? So I've identified all of my numbers, right?
You don't have the standard deviation.
I do not have the standard deviation for my sample. Do I need it? I do not. Okay. Now, which of these two formulas on the board should I be using?
Right.
The one on the right with the star. Okay, this is the one, remember I told you to always use this one when you can? Now we really need to use it, okay?
Because it is the sample.
Yes. Okay. So, all right. So should she be concerned her patients are gaining too much weight? Okay. So I'm going to be using z equals x bar minus mu over sigma over the square root of n. And I'm going to underline this so that it looks kind of like I'm doing this. Okay, so my x bar is 36.2 minus my mu, which is 30. That's my numerator. My sigma is 12.9 divided by the square root of 35. So if I take this number divided by this number, I've got 2.84. Okay? So what I've just done, I've taken my population, which is right skewed. Okay? Now I'm going to insert. What is that? Oh, I thought it was a fire alarm. Thought we were going to have to evacuate. All right, insert shapes. I'm going to pick this one again. This time I want it to look normally distributed. Wow, that's a bad looking normal curve.
Looks good.
Pretend that's normal. Okay? And the idea here is, if it were normally distributed, insert shapes. Okay, so I've got a mean of, so this is my 36.2 pounds, and this is, let's say, insert shapes. This is my 30 pounds. Okay, so we're trying to decide, okay, if this area to the right here, I'm gonna, in fact, here's what I'm gonna do. I'm gonna shade this is really bad shading, but I'm gonna basically shade this stuff here. I'm trying to find the yellow area, essentially, of the curve. Okay? Pretend that it stops at the line instead of goes beyond there. Okay? Does that make sense? Would it be better if I drew this on the board? It would probably look better. Okay? So essentially what we've got going on here I've got the population, the mean is 30 pounds, okay? The sampling distribution is 36.2 pounds. I'm trying to find this area to the right, the red area here, okay? This is my p-value, area to the right. Okay, so what is that area here? How do I find that? We've got our z-score. So essentially what we've done is we've converted this so that the mean, instead of being 30, is now 0, and we are 2.84 standard deviations away. So we want to find this area here. How do I find that area? There should be two ways to find that. I think I only showed you how to do that with the chart last time, right? Okay, so with the chart, and I'll show you the second way today. with the chart, okay, so I've got the normal distribution here, okay? Notice my chart here, this is also in the back of your book. This is easier to see on Excel, so I've basically copied it into the book. And instead of it being 2 pages, it's all on 1 page now, okay?
That finds the area to the left of your Z, and then you have to.
So this gives me the area to the left, correct? So I want the area to the right. Okay, so I find 2.84. So 2.80123.4. Is that the right answer? 0.9977? To 1 minus that. Okay, so if I go back to here, so this is my z-score, and my p-value equals 1 minus 0.9977. Okay, so 0.0023. Okay, now the question is, how do you decide whether something's unusual or not? Okay, if it happens less than 5% of the time, it is unusual. Okay, is it less than 5%? Yes. Should she be concerned that her patients are gaining too much weight? Yes. Yes, her patients are gaining more.
So the population of women in general, her sample is women in a low SES neighborhood.
In a low income neighborhood,
Is
right.
that the low income people are gaining more weight, and it's probably because they don't have access to fresh produce and good food.
Yeah, they're going to McDonald's too much because it's cheap.
Well, because it's no big grocery store
Right.
neighborhood.
Okay. Now, let me ask you one last question. I kind of want to ask you two. What is the probability a single woman gains 36.2 pounds? Is this unusual? So all of my numbers are going to be exactly the same, right? Z equals X bar minus mu over sigma over the square root of, what's my n in this case? 1 woman, right? We're just doing 1 woman, not 35 women. Is it unusual for 1 woman to gain 36 pounds? So this divided by that.
Standard deviation is 12.9, so she'd still be within.
It's the same standard deviation we used last time, but we're doing 1 woman rather than 35. So you'll be able to see here, yeah, I mean, you can kind of compare. Look at this number. This number is way different than that number, right? Now, another thing to point out here, when you're doing a sampling distribution, let me stop sharing for just a moment. Okay. Notice the population has a lot bigger standard deviation than the sampling distribution. And I did that over here too. Okay. Sampling distribution has a much smaller population than the population. Okay. So you would expect your sample to have a smaller standard deviation. And that's why when we look at our denominators here, "35 women are going to have a lot smaller standard deviation than 1 woman. Okay, so my z-scores here are pretty different. I'm 2.84 and now I'm 0.48, right? 0.48 isn't very, that's a half a standard deviation, right? Now let me show you the other command. So I could use the chart. This is the chart. Now, there is another command here, and it's norm sdist. Now, there's two of them. One of them has periods, one does not. The one without the periods is the easier one to use. That's the one I would recommend, okay? Now, remember so I'm going to pick this z-score here, 2.84. Now, remember the chart gave me 0.9977. The computer gives me another decimal there, right? So the p-value here, so it works exactly the same way as the chart. It's going to be 1 minus this, okay? It's going to give me a little bit more detail because the computer's smarter, okay? So you can compare those two p-values and you can see that they're basically the same, okay? 0.0023 versus 0.0223. Does that make sense? Okay? And if I do this one here, you can also say 1 minus norm sdist, because I want to subtract this from 1. Oh, except for I haven't done this. No, that's right. 1 minus norm sdist of that number there. Okay? Which is 0.31. Is this unusual?
Nope. Yes.
No.
No, because it's at 31% instead of.
It's 30%. Remember, we're comparing this. If it happens less than 5% of the time, it's unusual. And this happens 30% of the time, so it's not unusual. So it's not unusual for a single woman to gain 36 pounds, but it would be unusual for 35 women to gain 36 pounds. Does that make sense? Okay. This is where interpretation is going to be coming in, okay? Now, just as a reminder, I was going to do one more problem. Do you want me to do one more really quick and I'll be done, or do you want to save it for the review tomorrow? Okay, so we'll save it for the review tomorrow. Do you guys want to go to the library tomorrow for class so we can use the computer? Okay.
Yeah.
Now, there's a really quickly, in case you run into any of these on the homework, because I'm out of time. I do want to give you one more equation here. Okay. This equation on the board that I used. Z equals x bar minus mu over sigma over the square root of n. Okay, that's got your x bar in it. The other formula that you may need for this chapter is going to be z equals p hat minus p over the square root of pq divided by n. Okay, that's going to be for your discrete data. This is going to be for your continuous data. Okay, so I've got two formulas. Basically, in both cases, you can think of it conceptually as the data minus the mean over the standard deviation over the square root of n. Okay, you can see the square root of n is in this formula as well. Okay, but we're using p's if it's discrete data, polling data. If you see percentages or proportions, you're going to use this one. If you see means, you're going to use that one. Okay. So if you have any questions on this tomorrow.
Proportions, you're going to use the first one, right?
Proportions, you're going to use the second one. For means, you're going to use the first one. Okay? So if you see percentages, use this one. If you see means, use that one. Okay? We'll finish that off tomorrow in our review, and so I'll see you all tomorrow.
So what kind of things?
So the test will be on, well, there's a quiz and a test tomorrow. If you want to take the test tomorrow, you can. The quiz tomorrow is going to be chapter 15. The test tomorrow will be chapters 3, 4, 5, 12, and 15. Okay? All right, we'll see you all tomorrow.